So we now prove monotone convergence theorem without using sigma additivity. So this is the true proof of monotone convergence theorem. So the first thing to notice if we have an increasing, non-decreasing sequence of functions is that, of course, each term of the sequence is bounded from above by the limit of the sequence. So Fn is bounded from above by F. And by monotonicity, which we have already proved, monotonicity, we can integrate this with respect to the measure. And this is still true, and this is true for every n. So we can take the limit in n, and we have this inequality. So what we really have to do is to show the opposite inequality. We have to show the inequality in this direction. So what we have to show, let's rewrite it, is this. And we can replace this integral here by what is its definition. What's the definition of this integral? This is the supremum of the integral of g over all g simple. So this is the definition, so we can compare it now with this definition instead. And now how can we compare this limit of integrals with the supremum? Well, if we can prove that this is larger than the supremum minus epsilon, or instead of doing minus epsilon, let's do something else. If we can do the following, let's move it a little more again. If we can show that this is larger than alpha times the supremum for every alpha less than 1, then we can take the limit as alpha tends to 1, and this will still be true. So this is what we are aiming at. We're aiming at showing this. And one more step is, instead of showing this, what we can do is, let's get rid of the supremum. Let's get rid of the supremum and instead write it here. We can write it here for every alpha less than 1 and g below f simple. And to prove this, we'll do the following. We define this set An to be the set of little omegas such that Fn of omega is larger than alpha times g of omega. So we have fixed g because we have to prove something that holds for every g. We have fixed one, and now we are taking this set An. Actually, we want this equal here just because in some places g can be 0, and we want to cover that case as well. So we have this sequence An, and now you note that the following. If f of omega is positive, then g of omega, g which is alpha g of omega, is strictly less than f of omega. And the strict inequality, because this number is positive, and this number is less than 1, and g is less is at most f. So this for omega such that f of omega is positive, we have this, but since Fn of omega increases to f of omega, there exists an n such that Fn of omega will have to be larger than g alpha times g of omega. I'm putting more than or equal to here. Actually, you have strict inequality if we want, but it is not very helpful because now we have to consider the other case, which is for omega such that f of omega is equal to 0. We have g of omega has to be 0, fn of omega has to be 0. We can also multiply by alpha if we want. It will not change anything. Hence, Fn of omega is still larger than alpha g of omega. And now this is for every n. This is for every n. Whereas before, it was there exists n0 such that this holds for all n larger than n0. So in both cases, we have this set here for all n large enough, Fn will be larger than alpha g, which means, so all this argument is just to say that this set here, which is this sequence, which is obviously non-decreasing, because these functions, they are increasing more and more. So once omega belongs to an for some n, it will continue to belong to an for larger values of n as this function fn is increasing. So all this argument below here is just to say that this set increases and it increases to omega. And we can say it increases to omega because for every little omega, if we are eventually in that set. And now remember, we're trying to compare these two quantities. So what I'm going to write is, let me copy here the integral of fn. Fn is a non-negative measurable function, extended Borel function. We're integrating fn with respect to mu. We can compare, we have already proved monotonicity of these integrals. This is fn times a function which is either 0 or 1. So multiplying it by f will produce a function which is at least as large as f. And this function, which is either 0 or 1, will be exactly the indicator of an. So this is a function which is 0 when an for omega, which is not in an, but 1 there. And why do we want to do this? Because, well, on this set an, we know that fn is larger than alpha times g. And outside the set an, it doesn't matter because we have 0 here anyway. This is the dirty trick that appears in this proof. So, which means we can replace this by alpha g indicator of an. And this is very convenient because the only term here that depends on n is this indicator of an, but an converges to omega. But we cannot use monotone convergence theorem, not yet, because this is what we are proving at this point. So we have to kind of prove it, but by brute force, by hand, which is, this is a simple function, and we already have properties for simple integrals of simple functions. We already know it's linear. Only for simple functions we have proved. We have not proved in general that the integral is linear. So being linear means this alpha gets out. Alpha gets out. And now what's the definition of this g times indicator an? Well, this will be the sum over j, or aj. Aj are all the values that g can take. Then the measure of the set where this function takes this value aj, and what will that set be? Well, that will be exactly the set omega such that g of omega equals aj, but now we're multiplying by this ugly indicator here, so we have to add a condition which is omega belongs to AN. Have to add that condition as well. And this is exactly the measure of the set where this product here takes value AJ for AJ different from 0. For AJ equals 0, the measure of the set does not matter because it's being multiplied by 0 anyway. So we have this, and now what we use is, this is a sum, a finite sum, so this is going from 1 to k for some k, and it's a finite sum of multiples of measures, and now we can use continuity from below for measures. And this is what is behind the monotone convergence theorem. So we can take a limit. Let us replace this. So I just copy exactly the same thing again, but now let's replace this equal here by a limit, and the limit as n tends to infinity. So when n tends to infinity, what's happening here? This is not n, this is k. What's happening here when n tends to infinity? Well, remember this set an, it converges to all of omega. So this is an increasing sequence of sets, and measures are continuous from below. So when we take the limit, this just disappears. And now if we observe well what this expression became, is this is simply alpha times the integral of g, which is what we had to do. We had to compare this with this, and it's fine. We took a limit, and we showed that that limit is larger than that. So this concludes the proof of the monotone convergence theorem without using sigma additivity. And it also concludes this video lecture.